I'd like to start with a very simple definition, which is that progress in any given technology is simply the number of iterations times the progress between iteration. In this session, I will be talking about how a convergence of digital technologies has led to numerous advances by significantly increasing both terms here, the number of iterations that can be done, as well as the progress that can be made between iterations. While this session will go deep into technology, I promise you that this is the one and only equation that you will see during the course of the session. So three fundamental digital technologies have converged to create an ecosystem. The first of these is NVIDIA's invention of the GPU. The GPU really lies at the heart of modern artificial intelligence, whereby this technology, because of the amounts and vast quantities of data it can process, acts as the brain of computers, robots, self-driving cars that can perceive and understand the world. The second is cloud infrastructure. And what cloud infrastructure has done is it has taken the advanced capabilities of GPU computing and hardware and made it very widely accessible and affordable. And this is especially important for smaller companies and startups that are the source of much of the innovation that we see in the world today. The third is advanced simulation software, and this is where my company, CPFD Software, integrates into this ecosystem. We were a very early adopter of GPU technology, and to give you some idea of what that has meant, we are able to run simulations over 1,000 times faster than we were able to do with previous generations of computer hardware. What this means, for instance, is that a simulation that in the past may have taken a month to complete can now be done in a few hours. So before we go into the energy industry, let's for a few minutes just consider how these technologies are having an impact on other industries. And the industry I've selected here is the aerospace industry. Now, we're living through a very interesting time in aerospace because a number of private companies have used digital technologies like the ones I described to become the leading innovators in a field that is space exploration that was once exclusively the domain of national government agencies such as NASA that had access to vast amounts of funding. To take an example of SpaceX, SpaceX is now on its 7th rocket version, and it has used digital technologies to reduce the development time from 6 years to about 2 years, which is a significant improvement. But let's now talk about a true startup in this industry. And the company I've selected over here is a company called Boom. Now, Boom is developing a supersonic passenger jet, and it expects to do so in half the time and at a fraction of the cost of the last supersonic jet, which was Concorde. And to give you some perspective here, Concorde took 30 years and over $5 billion with a lot of support from the governments of the United Kingdom and France to bring to the market. So let me repeat, Boom is a startup company that is developing a supersonic jet. And one of the reasons it's able to do so is through the use of computing and simulation. And one of the most important simulation methods that Boom uses is that of computational fluid dynamics, or CFD. And what this does, it enables the engineer that is working on the design of the aircraft to make the aerodynamic design on a computer rather than the old way, which was through building a physical prototype and then testing it in a wind tunnel. To explain to you what this means in practice. If you take a passenger aircraft, a 5% reduction in drag translates into 500,000 gallons of fuel consumption, which in turn means about $3 million in cost reduction per year per aircraft. Now, what Boom is able to do is use CFD simulation to go through hundreds of designs of aircrafts, select the best one, and move on to the next iteration. To date, this company has already run 66 million hours of compute time testing and testing the design of various aircrafts. While aerospace was the first industry to widely adopt the use of CFD, it was followed very quickly by the automotive industry. And today, in both the automotive and aerospace industries, CFD has become an indispensable part of the design. And what it has done is it has largely replaced what you will see here, which is wind tunnel testing, which was the old way of doing things. In fact, the sport of Formula One racing, which has historically been one of the biggest users of wind tunnel testing, is currently considering a complete ban on the use of wind tunnel testing for Formula One sports teams, primarily because CFD results are very accurate, but as well, wind tunnels such as this are very expensive to build and operate, and they have significant environmental impacts. So now let's now step into our world, which is the world of energy and energy-intensive industries. And this is where things actually get far more complex and challenging. The examples I gave you from aerodynamic design are actually a relatively simple CFD application. And the reason for that is you are dealing with a single-phase flow, namely that of air flowing over an aircraft body or a car. When dealing with energy systems, we are often dealing with multi-phase flows because inside of a reactor, you could have liquids, solids, as well as gases. You've got to consider the mixing and turbulence of those flows. There's phenomena like heat transfer, mass transfer. A lot of these reactors are running under conditions of very high temperature and pressure, so things like thermodynamics, catalysis, reactions, those are all important phenomena that need to be considered. And this is where my company, CPFD, has developed a software package called Barracuda Virtual Reactor, which integrates all of these different chemical and physical phenomena to serve the needs of the energy and energy-intensive industries. And this video over here gives you an example of one such simulation. This one is taken from an FCC riser. And I'll talk more about FCCs in a later example. So let's now consider some use cases. And the first one is that of the scale-up of the Sierra waste-to-biofuel plant. This is an aerial image of the Sierra biorefinery that was constructed. The construction was complete in July of 2021, so it's very new. It is located in the state of Nevada, very close to Reno, here in the United States. And this is the world's first garbage-to-jet fuel plant. It was constructed by a company called Fulcrum Bioenergy. And when it is fully operational later this year, it expects to convert 175,000 tons of municipal solid waste, essentially trash, into 11 million gallons of renewable biofuel per year. Now, at the very heart of the Sierra biofuel plant process is a unit called the gasifier. And what happens in this particular unit, you'll see it here in the diagram on the left, is that the feedstock which is the trash, enters and is ultimately converted into a synthetic gas after going through multiple gasification units. This is the most complex and challenging part of this process. That synthetic gas is later converted into liquid fuel. And what you'll see here is a picture of the process demonstration unit that was used for testing this before taking it to the fully commercial level. Now, a lot of very promising technologies that get developed in labs, one of the biggest challenges is scaling up. In fact, for many chemical and process-related technologies, the valley of death is really that scale-up process. They could work very well in a lab environment, delivering good yield, but when it's taken to the full-scale level, that is when a lot of technologies do not deliver what they were intended to do, and consequently are never commercialized. And the reason for this is in this scale-up process, there are numerous variables and factors to be considered. So to give you some example, when you're scaling up a chemical-related process, you've got things such as the unit design parameters to consider, the height, the width of the unit. You've got the staging of various internals. You've got feedstock parameters. You've got operating conditions. And if you were to consider a unit with, let's say, 10 variables with 3 options for each, if one were to test all of the possible configurations, one would need to conduct nearly 60,000 tests, something that would be impossible in the physical world, but it is feasible in the digital world. And that's exactly what Fulcrum Bioenergy and its partners did with the Sierra plant. And what you will see here in this video is one of those simulations that was run using Barracuda Virtual Reactor. And the end result, or the conclusion I will tell you from this, is that the scale-up of this very novel technology would have been impossible without the use of digital simulation and testing. If physical testing was required, this would never be developed in a commercially relevant timescale. So let's move on to another example here. And in this case, I'm going to talk about the troubleshooting and optimization at a refinery. What you will see here is an aerial view of the Geelong refinery. This is a refinery that is located in the state of Victoria on the southeast coast of Australia. And it is operated by the company Viva Energy. It is a 120,000 barrel per day refinery. And what you will see here on the left is a picture taken from a turnaround that was conducted at the refinery back in 2016. This turnaround was a very vast undertaking for this refinery. It required 2 years of detailed planning. It involved over 1,000 personnel, and it ultimately cost over $100 million. And what I've encircled here in red, you'll see it here, is the fluidized catalytic cracking unit, FCC for short. And sometimes you might have heard it referred to as the cat cracker. This particular unit, the FCC, lies at the very heart of any modern refinery. It is a very high conversion unit, which is responsible for producing much of the gasoline, as well as a lot of the high-value petrochemicals like olefins in a refinery. So it's a very, very critical unit to a refinery. And just very briefly, if I could, I'll explain to you what's happening over here. So this is the main reactor. You'll see it in the diagram here. Also, it's the taller one in the picture. And what's happening in this reactor, as the name suggests, it's a fluidized catalytic cracking process. So cracking being breaking the larger chains of hydrocarbons into smaller chains by use of a catalyst that is fluidized. During that reaction, the catalyst gets coated with carbon as it is used in that reaction. That spent catalyst then gets transferred over to another unit over here called the regenerator. And you'll see it here in the actual picture there. Within the regenerator, that catalyst undergoes a combustion process whereby the carbon is essentially burnt off, and that catalyst is also heated during that combustion process. That catalyst is, by doing so, it's then reactivated. The reactivated catalyst is then circulated back to the main reactor for use for the process again. So the real elegance of this system is that it's a closed-loop system, and these FCC units, they're the real workhorse of a modern refinery. They run 24/7, 365 days a year, often for durations of up to 5 years, and under conditions of very high temperature, over 1,000 degrees Fahrenheit. The units take a real beating because they've got catalysts circulating inside. So it's a very rugged and versatile unit. Now, in 2016, Viva was experiencing a problem within its regenerator unit. And that problem was excessively high temperatures. And this was a concern because at above 1,400 degrees Fahrenheit, one starts to approach the metallurgical limits of these reactors. So to identify the root cause of this high temperature, Viva used simulation. And what you will see here is four concurrent simulations from that regenerator unit. So what you will see in this first one on the extreme left here is the circulation of the catalyst. It shows good mixing. It looks normal. The second over here shows temperature. And this illustrates the problem because you've got high temperature at the top of the reactor. And in a normal unit, this should be much more uniform, the temperature. You will see one cool spot here, and that corresponds to the injection of the spent catalyst into the regenerator unit. And so it's coming from the main reactor. It's been cooled, and then it's heated up during the regeneration process. It shows the oxygen concentration. And what you will see here is oxygen is injected into the unit from the bottom. So concentration is highest here, and it decreases as it's being used up in the combustion process. But it is this last one that is the most telling simulation. And what you see over here is carbon monoxide. And what you will notice is that the carbon monoxide concentration is concentrated on the left, and as well, it is rising up in the unit, which shouldn't be the case. The carbon monoxide should decrease, and there really shouldn't be any carbon monoxide at the very top because it should be converted into carbon dioxide. So based on this information and the results from a number of other simulations that were part of this study, Viva was able to identify the root cause of the problem, which had to do with the manner in which the spent catalyst was distributing, the spent catalyst was entering and being distributed within that regenerator unit. And so based on the simulation, they were also able to test various design modifications and ultimately select the best design that was then implemented at the time of turnaround. And this solved the high temperature problem. What it meant in terms of the performance of the refinery was that they were able to increase their throughput by 4%. Prior to the turnaround, they were moderating their throughput in an attempt to lower the temperature. But by operating with this higher throughput, that 4% in economic terms, using today's pricing, translates into $10 million in annual profitability for a refinery such as this. So lastly, I'd like to talk about the future and what we're seeing right now is that a number of companies and laboratories are using simulation for fundamental R&D. They're using this to test, design, and scale a number of technologies that will be essential to our energy transition. And so we have experienced the use of simulation for ammonia, biofuels, carbon capture and sequestration, cement production, chemical looping combustion, emissions control, energy storage systems, gasification, hydrogen, polysilicon, pyrolysis, recycling of plastics and batteries, and the waste conversion of energy to fuel, the waste conversion to energy, fuel, and chemicals. One of the things that I'm very optimistic is that, as opposed to the past, where it was largely big multinational companies that were undergoing this research, what we're seeing now is a large number of small startup companies that, using advanced computing with cloud infrastructure, are able to undertake fundamental R&D in these fields. And that leaves me very encouraged about the future. So to conclude, I hope that during the course of this session, I've been able to explain to you how engineers today are able to use digital technologies to advance technology by increasing both the number of iterations they can perform as well as the progress that can be made between iterations. Thank you.
Thank you, Mr. Rajat. Now we are open for the Q&A. Please raise your hand if you have a question so I can hand you the mic.
Can you talk a little bit about the work you're doing in plastics recycling?
Sure. That's a very interesting and very new application. So let's talk about what plastic recycling has meant in the past. Traditionally, we all recycle our plastics and put it in the recycle bin at home. But in reality, historically, very little of that is actually recycled, because during the process, the historical process of melting and extrusion, the quality of that plastic degrades very significantly, and very little of it is actually used and converted into a recycled product. What's happening in the world today, which is very, very exciting, is that chemical processes, which are much more similar to what you would see in a refining unit, whereby you're taking larger hydrocarbon chains and cracking them, those are being employed to chemically recycle plastic. A lot of this is being done in fluidized bed reactors, and there are a number of companies, as well as universities, laboratories, that are engaged in this research. And I'm very pleased to say a lot of them are using digital simulation combined with GPU hardware and cloud infrastructure to really bring these technologies to the market in a commercially relevant timescale.
Thanks for the presentation. Are you doing anything, I know you talked pretty purely about simulation. Are you doing anything with like real-time data integration or sensor integration within your simulations?
So not yet is a short answer. Not yet. I mean, there's a lot of talk about digital twins, for instance, and that would give you a true digital twin. We're not quite there yet. Part of the challenge here is that some of the reactors that we're dealing with, like let's take the FCC example I gave before, you're talking about temperatures of 1,000 degrees plus, so there's very little sensor information that you actually have inside of the unit. So that's one challenge, but this is something that's being worked on. We're not there yet, but I do expect to see that in the future.
In this example that you showed for the FCC, the regenerator, to understand that the CO distribution, did you use mainly the temperature profile that you got from the unit to calibrate the model? So how was the process to calibrate the model?
Yes. So essentially, there are certain types of data you're able to obtain from sensors. So in the case of this, you can basically surround the unit with temperature sensors and use that as part of the input. So yes, that was employed as one of the inputs. And in our early days, a number of the simulations were physically validated. This technology has progressed to the point where, particularly in the world of finding some of the more established applications, that validation is no longer being done. But definitely in the early days, the validation was a very big part of the process.
So for each one of the applications that you were showing, so let's say future, you take another use case. How much time on the average does it take you to build a model or build the simulation model of this?
Yeah, so good question. So our simulations are very complex, and this is something that a lot of people have a very hard time understanding and grasping. So a simulation can, the most complex and challenging simulations can run and used to run for many months, even over a year, one simulation. And this is where, of course, the advent of GPU computing has really made a world of difference. So I'd say there's no one answer I can give you to that. It really depends on the type of unit, the complexity. Let's take FCC. Those are simulations that we can run very quickly. It also depends on how we're set up, because a lot of times refiners will run a baseline model. So if the baseline model exists, we're able to react very quickly and do it. We already have a lot of the inputs and the parameters. We're able to turn it around in a day. One of the biggest bottlenecks, if I could put it that way, in running a simulation is actually not necessarily the simulation itself. It's that process of gathering the data, things like the CAD design for that unit. If all of that is available, then we can turn it around very, very quickly, matter of a couple of days.
Thank you.
What are you looking for from us? Are you looking for clients, or since Schlumberger doesn't like the word clients, perhaps customers? Are you looking for venture capital or something else?
So primarily what I wanted to do in the course of this presentation was really build awareness of the capabilities of simulation. Historically, the oil and gas industry has been a relatively slower, if I could put it that way, adopter of technologies for a variety of reasons, right? It's a risk-averse industry. You're dealing with conditions of safety. So it has been a relatively slow adopter of technologies. What I wanted to primarily impress upon the audience over here is that this technology has advanced to the level that it has become quite mainstream. So we are looking to build awareness, looking for customers, and we cover such a wide range of applications that we don't know what the next application would be. So if there is someone sitting here in this audience who has an application I haven't talked about, come and talk to us. So we're not looking for funding. We're fairly we're a software company, so our business is not very capital intensive. So really what we were hoping to do here was to build awareness and build up the client base, as well as make people aware that this technology can be used for a lot of the novel technologies that are being talked about in the CERAWeek session. So all of those technologies I've showed you on that last slide, there have been presentations throughout this week on each of those. And many of those may not know of the capabilities of simulation today. So this is a field that's progressed significantly and continues to progress.
All right, great presentation. It's kind of a follow-up question that someone asked, basically that you don't really have to post-validate as much as you used to. Mm-hmm. Could you expand, why is that?
Well, it really depends on the application. So what I was referring to there was primarily refining, because the we've done enough validations that, that the operators of refineries have become very comfortable with relying upon simulation. So really the technology has progressed to the level that the simulation results are trusted by the operator. So because these simulations are very hard for people to grasp often, let's go back to CFD, aerodynamic CFD, for car design or airplane design. That is hardly ever validated because that technology has progressed to the point. I gave you the example of Formula One racing. They're going to ban, they may ban wind tunnel testing. So they may ban the validation process because that technology has progressed. Similarly, for certain applications, this technology has progressed where validation is no longer being done.
So you answer about real-time optimization, but I would like to know if you have any approach in terms of eliminate pilot plants in a chemical process, using that simulation to test batches instead of going there.
Thank you. So look, in many ways, that is the holy grail, actually, because if you are able to take a lab process and avoid that pilot scale process, which is time-consuming, very costly, and go straight to the commercial phase, that will unlock and deliver immense value for the chemical and process industries. And what I can tell you is that there is currently a company that is working on plastics recycling here in Houston. In fact, I can give you the name of a company called Encina Chemical, that is using this. And with this technology, they are looking to completely avoid that pilot scale process. So that is very much a work in progress. And this is, stay tuned. This is a story that I hope to be able to tell in the very near future.
Rajat, you used the word reactor, so my obvious thought goes to nuclear reactors.
Right.
And so have you looked at simulating the conditions in a nuclear reactor? Mainly, there's a lot of paranoia regarding nuclear energy, so some things can be done to remove that fear and paranoia from nuclear.
So short answer to your question is yes. The longer answer is yes, but not by us. Because, so let's take a step back. What I didn't cover in this talk is that the company actually originated from the Los Alamos National Laboratory in Albuquerque, New Mexico. For those of you who are not familiar with Los Alamos was the birthplace of the Manhattan Project, which is where the nuclear bomb was developed and tested during World War II. It also happens to be the birthplace of CFD, the field of computational fluid dynamics. So the technology actually has been applied in the nuclear field. The more complex answer is that it has been applied by various national government labs. I can tell you, like the Department of Energy and labs run by the Department of Energy. And so this is information that we're not privy to, unfortunately. Those labs, it's publicly known, do use our technology. But how they use it and what they do with it, unfortunately, we do not know. And probably for the best as well.
Okay, thank you guys. That's all time you have for today. So thank you for joining us. If you have more questions, he'll be happy to stay on and then answer some questions. So please stay, and thank you for joining us. Thank you.
Thank you.